Yes. Okay. Good. Okay. Hello, everyone. Welcome to another lecture seminar in computer architecture. Today, lecture 6, we're going to discuss about storage-centric computing. Before I jump to this lecture, we have already released a list of papers, and I have to remind you that basically show your preferences by, I don't know, by Tuesday. I think that's the deadline. We will schedule the students' talks hopefully after that, when we observe your preferences. Okay. Basically, the problem that I'm going to discuss today was also similar to the problem statement that Geraldo was presenting last week about memory-centric computing. But today we're going to focus a little bit more on storage because we see that for some applications, it's really important that we also benefit from storage-centric computing, as you know, the amount of data that we have to move to the processor is quite huge, and we are bottlenecked by that I/O data movement. So, but yeah, again, the problem is about that computing is bottlenecked by data for modern applications, and data is key for AI, ML, genomics, many important applications. And you know that basically important workloads are all data intensive these days, and they require rapid and efficient processing of large amount of data. And data is increasing, so we can generate more than we can process. And that's the problem that we have today. Many devices that we have that they are generating, basically they are data generators. They generate more than we can process. And that's one of the reasons for that is that data generator machines are usually customized machines. So they are specialized systems that they are customized for generating data, but unfortunately, when we want to process them, we are using general purpose systems. So we really need to look into this problem. So I'm gonna flash some slides about the motivation of the slides, because I think you have already also seen them in the previous lecture, some of them. But this is the data that Cerebras team, they actually presented in one of the Safari Lab seminar. So you can see that actually 4 orders of magnitude increase in memory requirement in just 2 years. And also around 3 orders of magnitude more compute in just 2 years. So that shows actually the problem of the need for higher computational throughput, as well as the higher for storing this huge amount of data. And so data is also key for future workload, like in-memory database, graph, tree processing, data center workloads, in-memory data analytics. And you know, basically data is bottleneck and for performance and energy. And if we want to basically make sure that we provide good performance and energy consumption at the same time, we really need to handle data well. So this is also another example that I really like it. I think you have seen that this slide in genomics presentation as a lecture. But basically, before 2007 or so, the throughput of the data sequencing machine that basically so-called as a data generator for us was more or less, aligned with the performance of our computing systems. But then, from 2000, as of 2007 and after that, basically, we had huge improvement in throughput of sequencing machine. And unfortunately, we see that huge gap between basically the throughput of the computational system and this data generator system. So, and basically in order to, this genome analysis includes many different applications, like for sequencing machine that we also need to do some, for some of this technology, we need to do so-called this base calling, which is a high computational intensive application to translate raw electrical signals to ATCG, and also this read mapping process, variant calling, and in the end, scientific discovery. So all of these are data intensive, and basically performance and energy are bottlenecked by data. So basically, we need faster and scalable genome analysis. I mean, this genome analysis here is an example, so you can actually consider any nowadays data intensive applications. In order to have better understanding of genetic variations, species evolution, predicting the presence and related developments of microbes in the sample, and having basically, stop these disease outbreaks, and in the end, also developing personalized medicine, which is quite important these days. So, and many other applications. So, when you provide much better performance and energy efficiency, it's not only about faster process. It's also about enabling applications that they were impossible in the past, but now we can hopefully get to them. So this is what I also discussed about it just a few slides before. So we have this special purpose machine for data generation, which is fast, but unfortunately, when we want to analyze this data, we are using general purpose machine, and that is slow. And this picture is similar for many data generators and analyzers today. So that's the thing that we really need to also look into, the systems that we are designing today for analyzing data. So unfortunately, data overwhelms modern machines in many aspects, like storage and memory capabilities, communication capability, and computation capability. And as a result, we greatly all these impacts robustness, energy, performance, and cost. And in order to provide good performance, energy, and also reliability in general, and also low cost, we need to design new machines. So let's quickly also have a recall. I just like to jog your memories about what's the reason about all these issues that we have today. So it's about the computing system that we have designed for decades and decades, like these three key components: computation, communication, and storage and memory. And this is the von Neumann model that you are aware of that. And basically, we need to load data from memory systems to the computing unit through this basically memory storage unit and then communication unit to the computation, like the processor. And we can analyze them and then store them back to the memory. So you can see that we need to move data a lot. And all the computation is just happening in one place, which is not really intelligent. So, and most of the system is dedicated to storing and moving data as a result of this von Neumann model. This is, for example, the processor design, the processor-centric design that we have today. You can see that we have basically different levels of cache hierarchy, like the shared L3 cache, shared L2 cache. Inside the cores, actually, we also have L1 caches. We have like big register file, so many other things. And also, we have DRAM as a shared memory and also storage. So this is the problem that we are observing because of this von Neumann model. And but unfortunately, still beyond, even though we have all these units to hide latencies and hide data movement, still systems are bottlenecked by memory and data movement. So basically, vendors, they try to alleviate this problem by deepening this hierarchy as much as possible using larger caches. But unfortunately, still we have this problem. So these solutions can be considered as, let's say, short-term solutions, but they are not necessarily sustainable solutions. So we really need to look into much better solutions, like the fundamental solutions to this problem. This is also this AMD 3D last level caching that proposed in 2021 that they use like 3D layer cache to have higher capacity for L3 cache. But yeah, you can still see the problem of data movement. And yeah, this is also Apple M1 in 2022 that you can see a lot of strand DRAM and also storage that basically we have in these architectures. So we really need basically look into intelligent architectures to handle data well. And how to handle data well? Basically, we need to ensure three important aspects. One is that we need to ensure data does not overwhelm the components. So it needs like new algorithm design, new architecture and system design, like the hardware software co-design, and also algorithm architecture devices. And also we can take advantage of vast amounts of data and metadata. Now that we have huge amount of data, why not using them in order to customize our systems on the fly? This is really important that I'm gonna also talk about it a little bit in this lecture. And also it's important to understand and exploit properties of different data. So hardwares in the past, conventionally, they usually treat all data the same, but in reality, data are not the same. Depending on the which applications, these data belong to. And so if we can somehow transfer the semantic of data to the hardware, we can make much better decisions. So basically, we think that computing systems today are processor-centric, but we really need to get to data-centric. That a big part of this lecture is about data-centric computing, which we mean the process where data resides or process where it makes sense. Also, we want to make, instead of making these designer-dictated decisions, we want to make data-driven decisions, like using some machine learning algorithms, like reinforcement learning agent, for example, to adapt our policies on the fly. Also, so in order to make component-based myopic decisions, we want to have data-aware decisions. So the semantic of data should be transferred well to the hardware. And in the end, so in order to have fundamentally better architectures, we need to ensure data-centric, data-driven, and data-aware architectures. So basically, in order to achieve that, we need to revisit the entire stack of computing from the algorithm to the device, and hopefully we can get there step by step. If you want to learn more about this topic, I would suggest that you check this paper from Professor Mutlu, Intelligent Architectures for Intelligent Computing Systems. Okay, but today I will mostly talk about data-centric architecture with the focus on storage. So this is all about processing data where it makes sense. Sometimes it actually makes sense to do it inside the main memory. Sometimes it makes sense to do the process or computation inside the storage. Sometimes you really need to do actually in the GPU or CPU. So it's about combination of all these computation capability that we have in our today's systems. So basically, I'm just about some more reminders that we have a lot of memory, SRAMs, storage in today's systems, and why aren't using them for computation? So this idea is actually is not new, it's actually relatively old. It has been proposed in 1969 in this paper and maybe also earlier. But the thing is that nowadays this idea is actually quite a lot more important, and we need to revisit this a lot because of many reasons actually. So today applications are much more data intensive, so we are really pushing the bottlenecks now, pushing the limit, and also we have also a lot of technology advancements. So these days, so now we have more opportunity to consider these applications. And of course, the memory and processor gap is getting larger and larger. So it's really important that we revisit this idea and enable it by new technologies, new ideas that we can develop in this area. So one of the reasons that I think it's really also important to revisit such futuristic idea, at least it was quite futuristic in 1970, is that today we cannot really trade off performance for energy or something like that. We really need systems that they are high performance, energy efficient, sustainable, all at the same time. So we really want everything together, and for that we need actually a huge jump in the way that we are designing systems. So again, the problem is that data access is the major performance and energy bottleneck, and our current design principles cause great energy waste and also great performance loss. And basically, processing data is performed far away from the data. So yeah, it's just as a reminder, it's about the von Neumann model that we basically have a lot of memory and storage, but we do computation only in the processor. So we need a paradigm shift to enable computation with minimal data movement and compute where it makes sense. This can be where data resides, but of course, there are also some applications that you need to consider some other source of also computing. And also make computing architecture more data-centric in general. So this is our goal. This is just an example of how the system can be look like the processing inside memory or storage. So you have like processor, caches, and also you have storage or memory that you can actually store your data, like database, graphs, media, or anything like that in the storage, and also together with the computation and the application code. And what we are envisioning as an example here is that basically processor only sends some queries to the memory or to the storage, and the storage of the memory just do the computation and send back the results to the processor. And that can save a lot of data movement energy and also provide much better performance. But there are many questions here, like how do we design the compute-capable storage memory systems, basically? How can we do computation inside storage or memory? Or basically, how do we design the processors and communication units? How do we design the software and hardware interfaces, system software, compilers, languages, as well as algorithms and theoretical foundation? So one of the important things actually I think we need that more going to the future is actually new algorithm design, and also some sort of new evaluation for algorithmic complexity, because the whole theory of algorithmic complexity is actually based on processor-centric design. Now that we have this area of data-centric, I think we also need more theory to how to evaluate the performance of different algorithms. So, but yeah, I mean, as a reminder, we need to revisit the whole computing stack in order to provide all these, basically, in order to provide good answers to all these questions. And yes, we need to think differently from the past approaches. So, in order to do processing inside the storage, we can actually have two common approaches. One is that in today's storage, we have a flash memory. So one approach is that doing processing inside the flash memory, like in-flash processing. And the other approach could be processing near flash memory. So inside the storage, you have basically your storage is actually a subsystem, it's a system design. And you have DRAM, you have multi-core system. So you can actually have some possibility to do computation close to the flash memory. So I will start with in-flash processing, but we will also get to processing near flash memory later. So the approach one is actually very similar to processing using memory that you have seen last week, I guess. So you already are aware of some works that we have done here, like we can exploit internal connectivity inside the main memory, like the DRAM, in order to move data. We can also exploit analog computation capability and so on and so forth. So there are many examples that we have done and proposed here. I don't have many of them, honestly. There are many also more recent work that we have done in this direction. But basically, like row clone, in-DRAM, and more gather scattered DRAM, and so on and so forth. So there are many research directions in processing using memory inside the main memory. Like Ambit is one of them that we propose how we can do in-memory accelerator for bulk bitwise operations. And after that, Nasser and Geraldo, they actually lead this paper called SynDRAM, that they design a framework in order to benefit from Ambit, like the majority operation that we can do. So in SynDRAM is a framework design that actually we can program using that primitives inside the main memory. Pluto is actually another work. So one of the issues that we have in processing using memory in general is that we are a little bit limited by the complexity of that computation. So usually the performance of processing using memory is limited, or the functionality is limited to only more or less the so-called simple computation. In this Pluto paper, we try to actually bridge that gap a little bit by providing support for LUT inside the main memory. And that can basically provide enable more sophisticated state computation. It's actually a beautiful paper, and I would encourage everyone to read it. And this one is actually how we can do in-DRAM true random number generation. It's another application, important application that we can enable using processing using memory. This is also Dr. Strange that is like the build on work, yeah, on top of Pluto. But yeah, so now I want to basically continue with the main purpose of this lecture. Like one of them is in-flash processing, how we can do processing inside the flash memory. And in order to go through this direction, I will use this paper, Flash Cosmos, that we published in Micro 2022. Any questions, by the way, before I jump to this paper? Am I going too fast? I will actually reduce the speed. Good to go? Good. So yeah, this is a Flash Cosmos, in-flash bulk bitwise operation using inherent computation capability of NAND flash memory. I will start with a short executive summary. So the background is that bulk bitwise operations are widely used in many important data-intensive applications like databases, graph processing, cryptography, etc. And so the problem is that these performance of energy efficiency of bulk bitwise operations are bottlenecked by data movement between storage and the compute unit in traditional systems, and also data sensing. So we will get to the definition of the data sensing. This is really related to flash memory. So we'll discuss about it in more detail very soon. But I would like to briefly describe a little bit more about this data movement problem. So these applications that bulk bitwise operations, the arithmetic intensity is quite low. So you need to basically load a lot of data, but you just want to, for example, and basically you cannot really amortize the amount of data that you're reading by that computation. So that's one of the reasons that these applications are heavily actually bottlenecked by data movement. And also data reuse is also very low. So there are many reasons that these applications are heavily bottlenecked by data. So there has been actually a effort on addressing this, accelerating these applications in processing using memory as well as processing inside the storage. But the scope of this work is actually processing inside the storage. And there was actually only one work that provide in-flash processing technique. But the problem was that this work provided low reliability during computation. And also prior in-flash processing technique, they are bottlenecked by data sets that we will see later. So the goal is to improve performance, energy efficiency, and reliability of bulk bitwise operations using in-flash processing. So our key idea is Flash Cosmos, flash computation with one-shot multi-operand sensing. So this technique is an in-flash processing technique that improves performance, energy efficiency, and reliability of bulk bitwise operations using two key techniques. Multi-board sensing that basically enables multi-operand bulk bitwise operation with a single sensing or read operation. And also enhanced SLC mode programming, which we propose for better reliability, that we will also see later. And as a key result, basically Flash Cosmos, we evaluated using 160 real 3D NAND flash chips, and it works perfectly. I mean, with high reliability, with good performance for all of them. And we also observed that Flash Cosmos improved the performance and energy efficiency by 3.5 times and 3.3 times over state-of-the-art in-flash processing techniques. So I will provide motivation, also some background about flash memory, because it's actually needed to understand better about this work. But so for motivation, I mean, we will actually also skip them quickly. But bulk bitwise operations, as I said, have been used in many important applications like databases, web search, genome analysis, graph processing, set operations, cryptography, hyperdimensional computing, and so on and so forth. But unfortunately, data movement between compute units and the memory hierarchy significantly affects the performance of bulk bitwise operations. So basically, data movement bottleneck here is that conventional systems perform outside the storage processing after moving data to the host CPU through the memory hierarchy. And that caused a lot of issues, basically. So in this figure, you can see storage subsystem, main memory, and the host processor, which can be CPU or GPU. So the channel that we have for storage to main memory, the I/O bandwidth is around 8 GB per second. And the channel we have from main memory to the host bandwidth is around tens to hundreds of gigabytes per second. And you can see that actually, and we do computation in the host. And you can see that basically the storage to main memory channel is actually a bottleneck by that throughput. It just actually talks about the performance issue, but there are also energy issues that you need to bring things from the storage. So for those processing using memory techniques that we are processing near memory, the idea is that the application data is actually resized in the main memory. But if your data originally actually stores inside the storage, and there is and it's not also worth it to bring your data to the main memory and do a lot of computation on that, you are actually bottlenecked by that I/O movement, I/O data access. And we believe that for actually for many of these bulk bitwise operations, we we end up actually be bottlenecked by this storage access. So yeah, as I said, the external I/O bandwidth of the storage is the main bottleneck for data movement outside the storage computing or processing OSP. So near data processing for bulk bitwise operations has been proposed and used for many prior work, like using cache, DRAM-based main memory, NVMe-based main memory inside the storage or in flash. But as I said, the focus of this work is actually for in-storage processing, which can be close to the flash memory, near flash memory, or inside the flash memory. Okay. So let's have a background on in-storage processing. So ISP, as short, performs computation using an in-storage computation unit. So this is very simplified figure of storage, and you can see that we have NAND flash chips, and they are connected to in-storage computation unit, which is actually so-called as a storage controller with some channels. So you can actually do computation, get read data from that NAND flash chips and do computation inside the storage controller, and then just basically we send back the results to the host system, right? So now we are actually bottlenecked by the throughput of the channels that we have internally inside the storage. And unfortunately, the storage internal I/O bandwidth is actually larger than the external I/O bandwidth. So in this example, is actually 9.6 gigabytes per second because we consider like 8 channels. But in actually some of these enterprise SSDs, we have up to like 16 channels, and it can actually go up to like 18 gigabytes per second or so. But in the end, yeah, we are bottlenecked by that, and we want to actually do computation with much higher performance. So storage internal I/O bandwidth is the main bottleneck for data movement in ISP. And by calling ISP, we really mean that so-called near flash processing that I mentioned, like the second approach. But we will discuss about it later. So in order to improve that bottleneck, in-flash processing is a technique that basically you can do computation within the flash chips as the data basic operands are being read serially. So now you can actually use all these flash chips to do computation, and in the end you just read the results and send it back to the system. So now, because as actually you have many of these flash chips, and in flash chip you have also a lot of hierarchy like dies, lanes, block, pages. So you have a lot of resources to do computation. So you can do actually computation with high throughput, and then you can just send the results back to the storage. So I'd like to actually mention this at the same time here. So I'm thinking of something like do some computation inside the storage and send back the results to the processor. So it's about reducing the amount of data, So if the computation that you are doing inside the storage can reduce the data, reduce the amount of data significantly, like summarize the data and send only useful information or something that we really need to do processing on the CPU or GPU, then you can actually observe a lot of good performance by using storage-centric computing. But if you want to do computation inside the storage, but you don't really reduce data, and in the end you need to send back your results to the whole things, to the process-centric, probably you're not going to observe a lot of good performance. So it's always good to think about it when you think about storage-centric computing. So yeah, so the in-flash processing is good, but unfortunately the proposal that this work has been we compared against that parabit. Basically, they have this data sensing bottleneck that we're gonna see. Why is that? So in NAND flash chip, this is also a very simplified version of NAND flash chip. So we have like pages, and imagine that in different pages you store different operands, right? So the proposal that we had in Parabit in Micro 2021 is actually a nice work. They basically control some latches that we have internally inside the flash chip, like C latch and S latch. I'm not going over the details of that. You can actually check the paper if you want. We can also discuss it offline if needed. But basically, you can do computation by doing serial data sets. So you sense or read. So in flash memory terminology, when we say sensing, it means reading data, basically. So we basically we read the first operand into the page buffer or sense. And by repeating this sensing and controlling some signals, let's say in that latching, you can actually accumulate. You can accumulate and, or you can accumulate or. So that's the way to handle it. So they can actually do several sensing and do basically AND operation. And you can see that here, if you want to do AND operation among 3 operands, you need to do 3 sensing, right? 3 serial sensing. And each sensing or each read process takes a lot of time because it's flash memory. Flash memory is slow. So you need to spend like, let's say 40 microseconds, for example, to read. So basically the latency for doing AND A and B and C is going to be like at least 120 microseconds, which is not really good. So serial data sensing is the bottleneck in prior in-flash processing techniques. And they also have these reliability issues in flash processing. So, sorry. So prior in flash, so basically, since you want to do operation inside the flash memory, you don't. So flash memories are well known as to be error prone. So when you read data from flash memory, usually it has a lot of errors, and you try to correct those errors by ECC, by using ECC. But when you want to do computation inside the flash memory, you cannot really do that because ECC is happening outside the flash memory usually because the ECC algorithm is quite complex inside for storage for flash memory, and it's not really efficient. It's not really cost efficient to do ECC coding and encoding inside the flash memory. I mean, there are some works that they do in ECC inside the flash memory, but they use very simple ECC techniques. But if you want to have good, correctability, error correction capability, you really need to use complex ECC techniques. But if you want to do that, you need to read data from flash memory, then do ECC and fix the errors and send back the data to the flash memory, and then you do the computation, which doesn't really make sense. So you really want to do computation inside the flash memory without doing ECC. So in this work, basically, they consider that, okay, we don't do ECC. And there is also another work like this is randomization. I mean, another, let's say, important functionality that we have inside the SSD, which is data randomization. So before writing data to the flash memory, we usually randomize data using a key, we scramble data, and that's actually because to avoid the worst case scenarios. So there are some data patterns that they can actually, exacerbate amount of errors. So we use that key and scramble data to avoid that worst case scenarios. And this is also good for security because it can be also some malicious program that they use that data patterns to destroy your data stored inside the flash memory. Again, if your data is randomized and you do computation on randomized data, you cannot really de-randomize it and get back the data that you need. There are actually some coding techniques that you can do computation on encoded data, like homomorphic encryption, if you are aware of that, but they are also very costly. So again, in this work also they consider that we don't do randomization. So basically, since there is no randomization and ECC support, we have errors. So basically, when we read operand A, basically there are some errors. And when you actually accumulate, there are more errors. And in the end, basically, prior in-flash processing techniques, they require the application to be highly error tolerant. And that's basically our goal. So our goal is to address the bottleneck of state-of-the-art in-flash processing techniques. So we want to get rid of this serial sensing of operands. And also we want to make it reliable, which is really important. So our proposal is that Flash Cosmos enables computation on multiple operands using a single sensing operation. So if you want to, for example, do and operation of ABC, you just do one sensing, and then you do this operation. And we want to provide high reliability during in-flash computation. So before explaining how we enable all these things, I will provide a brief background on flash memory. So a flash cell stores data by adjusting the amount of charge in the cell. This is basically based on the level of charge, which is the number of. Let's see if I have more detail on it. So basically the level of the threshold voltage. So in flash cell, it's actually a kind of transistor, but they add a floating gate, so-called floating gate, between the gate and substrate of that transistor. And basically, you can, when you want to program it, you apply a high voltage, and you trap some electrons in that floating gate. So basically, you cause some negative charge in that gate. And as a result of that, in order to turn on that transistor, you need to apply a higher threshold, a higher voltage. Basically, the threshold voltage is going to increase. So that's the way that we handle, this programming on NAND flash cells. So it's just about increasing and basically controlling the threshold voltage. And you can actually do it for with more finer grained, let's say, levels. But assume that we only want to have two levels, like 0 and 1. So 1 is usually considered as a raised cell that basically we don't have any electrons trapped in that floating gate. And basically, your threshold voltage is in the lowest value possible for that technology. It's like the nominal threshold voltage. But when you program a cell, you actually increase the charge, and basically you increase the threshold voltage. And we usually encode that state as 0. So a set of flash cells that are serially connected to form a NAND, they form a NAND string. So this is like the NAND string that we have, and they are connected to the same bit line. And the reason that we actually call it NAND flash chip is actually this NAND connection of it. So there is also another flash design which we call it NOR flash, that it provides a better parallelism. You have better latency for accessing your flash chip, but it has some overhead. It's quite complex. It's not really good for that density. So we don't really see much, NOR flash design nowadays. So when you want to target a set and you want to basically evaluate it is 1 or 0, you have some non-target cells. So for those non-target cells, some of them they might have been programmed already, which have higher threshold voltage. Some of them they may not. They may be still in the erase situation. So what you do is actually we apply a high voltage, like we call it VPass, and that VPass is high enough to turn on those transistors, regardless if they are programmed or erased. And for the cell that we want to target it, we want to evaluate that it's actually programmed or erased. So we apply a reference voltage, and that reference voltage is something between the two threshold voltage, because based on that you can actually evaluate that if that flash chip is programmed or is erased. So we apply a VREF voltage, and if basically the current flows from the bit line, we observe that that flash cell that we wanted to target actually operates as a resistor, which means that our reference voltage was high enough to turn on that transistor. And that means that basically that transistor, that flash cell was not programmed, it was an erased situation. So we encode it as 1. And if that's basically bit line current cannot flow, we conclude that basically did we, by the way, have a Bonnie event in the DDC lecture? No. Yeah. So if the current doesn't flow in from the beta, we observe that that flash cell is acting as an open switch. And that shows that basically we have programmed it already. Okay, so NAND streams connected to different bit lines, they comprise a NAND block. So you can see the block here. And each, so a row here, we call it word line, that controls a large number of flash cells, and that provides high bit level parallelism. So we can actually store one page or several pages in each word line. So if our flash cell considered as SLC, which has single level set, only 0 and 1, basically we store one page per word line. But it's also possible to store a higher number of bits in each flash cell by controlling that threshold window more accurately. And for with that, you will have basically you can store like 2, 3, or 4 pages in a word. And a large number of blocks that they share the same bit lines, you can see actually from this figure, they actually consider a plane. Okay, so from this figure, you can see that internally, the intra block, we have actually something like cells in the same block are connected serially, similar to digital NAND, basically circuit. And interblock, they are connected to bit line like in parallel, so they really like digital NOR. And that's the key insight that we have here to design flash cosmos. Okay, let me take the time. Yeah, I will finish Flash Cosmos and then we can have a break. So basically, the first idea of Flash Cosmos is multi-word line sensing. And let's see what it is. So this is actually quite simple. So intra-block, we have two kind of multi-word line sensing. It can be intra-block or inter-block. So intra-block, we simultaneously activates multiple word lines in the same block, and that causes bitwise AND of the stored data. So imagine that you want to, for example, AND 2 operands, like word line 1 and word line 2. Other word lines are they are non-target sets. So you just apply repass to all of them, but you apply vref to those word lines that you want to AND. And you can see that basically the bit line current will flow only if basically both flash sets are in the array situation. And that's exactly the definition of AND operation. So basically you can use this idea and do it for, let's say, for 4 operands, So here you can easily do AND operations for 4 operands. And that's the way we implement bitwise AND of multiple pages in the same block via a single sensing operation. So it's really simple, it's possible to do. For doing OR operation, we use interblock multi-word line sensing. Again, here we can see that we target basically here as an example, 2 word line in different blocks. And then basically the bit line current here does not flow, only both of flash cells here, they are programmed, they are considered as 0. And again, that is the definition of OR gate. And you can increase the number of operands here as well and do OR operations on higher number of operands. Okay, any questions? That's quite simple, right? Okay, but the thing is that we need to also do other operations, not only about AND and OR. So we also need to do fortunately in flash memory, we can, there is a possibility that we do inverse read. So if we store 0, we can read 1. If we store 1, we can read 0. So it's called as inverse read. So if you do multi-word line sensing intra-block, so you're doing AND. But instead of doing a read, you do inverse read. So you do NAND operation. Yeah, so inverse read is supported in modern NAND flash memory. And because of that, we can implement easily bitwise NAND and NOR as well, like exploit multi-word line sensing plus inverse read. And for XOR and XNOR, it's possible because we already have XOR between sensing and caches. This is also supported in flash memories. It's a patent on some papers that you can see here. So yeah, basically a combination of all these things, we can do a lot of computation inside the flash. Okay, now that we are done with that computation capability, let's see how we can make it reliable. So in order to achieve good reliability, we propose enhanced SLC mode program. But let's see what we really mean here. So this is a normal SLC programming. This is the distribution of threshold voltage for different cells that we have. So in order to read, actually, when I was talking about reference voltage, you need to actually apply VREF something here, right? So your VREF should be between these two states. We tested this and we showed that, okay, we program SLC in real NAND flash chips, but we actually, we didn't enable ECC and randomization, because in order to do computation inside the flash memory, you cannot really do ECC and randomization. Unfortunately, we observed that even in SLC programming, which usually provides high good reliability, I mean, imagine that today's SSDs are usually QLC. So these threshold voltage windows are basically categorized to 16 windows, 16 basically. And your margin gap is quite low, it's quite small. So it's very common to, have errors. But in SLC, actually, your margin is quite, wide, but still, with that also we have some errors. So basically, we conclude that SLC programming is not enough to do reliable computation inside the flash memory. And as a result of that, we propose enhanced SLC programming that essentially we try to control the programming step by increasing the margin. So we increase the program voltage a little bit, and we increase the voltage margin between the 0 state and 1 state. And also we control it more to make it sharper, so it's not that wide, And using this ESP, we observe that we can do computation with 0 error, basically. At least for the flash chip that we tested. We also consider some aging effect. We bake flash memory with high temperature, and we do some analysis on that, just to show that even some aged flash memory, they can also do reliably with flash classes. But for that, you can check the paper. There is a big, nice section, detailed section on that in the paper. Okay, so ESP improves the reliability of in-flash computation without the use of ECC or data randomization. That I would say is actually quite good achievement. Okay, so let's quickly also take a look at some results. So we, for our evaluation methodology, we evaluate flash plasma using both real NAND flash memory, like 160 real state-of-the-art 3D NAND flash chips. And basically, we validate the feasibility, performance, and reliability of flash classes. And we observe that, so the flash chip that we use, they are 160 48-layer 3D TLC NAND flash chips, but we don't really use them as TLC mode. So because in TLC mode, you can program flash chips in, so basically each set can store 3 bits, but we program them in SLC mode, which is, or let's say ESP, enhanced SLC mode program. So, and these are the number of word lines that we tested under worst case operating conditions, like 1 year retention time at 10K PE cycles. We didn't wait for 1 year. As I said, we use some, baking method, which is quite interesting to accelerate that retention time. And some worst case data patterns. So we observed that both intra and interblock multi-word line sensing operations require no changes to the cell array, which is quite impressive. So basically, our community NAND flash, they are capable of doing all this flash classes stuff. And both multi-word line sensing operations can activate multiple word lines. We observe that intra, we can do up to 48, And the reason is that the number of word lines that we had in that NAND flash chip was 48, per block. So we assume that if we have higher number of word lines or in a block, we can actually do AND operations up to, let's say, any number of word lines. I cannot say with high confidence because we haven't tested it, but at least so that the flash chip that we use, they had 48 word lines, and we actually, achieved 48 operands. But inter-block, because we have a higher current value, we were limited by the power and energy, and in the end, we couldn't do more than 4 blocks at the same time. So basically, the OR operations, we are limited by the number of 4 operands at the same time, but for AND operations, we observe actually quite a high number of operands that we can do operations. And we have a small increase in sensing latency, like less than 10%, which is also negligible for that purpose. And ESP significantly improves the reliability of computation results. We haven't observed bit error in the tested flash systems. We also evaluate 3 real-world applications that they heavily perform large bitwise operations. We use MQC simulation framework that actually Safari Group we have developed and released. So, and the workflows that we use is bitmap indices, image segmentation, and KP star listing. And for the baselines, we compare against outside the storage processing, like OSP. In storage processing that we do computation inside the storage controller, we call it ISP as short, and this state-of-the-art work parameter. So these are the results, and basically everything are normalized, I guess, to OSP outside the storage computation. So Flash Cosmos provides significant performance and energy benefits over all the baselines. You can observe it here. And so on average, for example, we could provide like 25 times better performance compared to ISP, and 3.5 speed up compared to parallel. And the same also good improvements for energy consumption. And so we observed that the larger the number of operands, the higher the performance and energy benefits. And that's the reason I was talking about how much you can really reduce the data. So for image segmentation, the application usually add on 3 operands. So add 3 operands, and the results will send to the system. So it's not a lot of reduction. It's just you reduce the data by 1/3. But for example, for bitmap indices or k-click star, you may actually. So it also really depends on how you configure those applications. We have detailed results in the paper. But for example, we have like AND operations of 256 operands or something like that. Or for example, k-click star, we have AND operations of 16 operands. So you really reduce data by order of magnitude. And that causes a lot of performance improvement. So if you want to learn more about this work, please check our paper on this QR code. And let's quickly summarize. So basically, this is the first work that enables multi-operand bulk bitwise operations with a single sensing and also high reliability inside the flash memory. And it significantly improves performance on average over parabit, ISP, and OSP. Like compared to outside the storage, we improve like by 32 times. And compared to ISP is like 25 times, and state-of-the-art is 3.5. As well as energy efficiency, we also observe very good improvements. And again, it's low cost and requires no changes to flash cell arrays. It does need some changes, let's say in the programming layer. So if you want to integrate this technique into your computing system, you really need to think about how you want to program it, how you want to use and communicate to the storage in order to do some computation. But from the side of flash memory, it can be implemented without any changes, which is really impressive. Okay, I think we can take like 5 minutes break, and then I will continue with some more interesting works. Yes.
This one, and then How you great. I'll just
That's it. Just the lecture. It's just for its history. And issue. So, the distribution that's so I already increased the last week. But they
you were just on it.
Yeah, because it was great. Yeah.
Can you explain how we are able to achieve not an XOR again?
Yes. Yeah. So for XOR, we already have XOR gates inside the flash memory chip. So we just need to use them, And for NOT operation, so I don't have it in this slide. I can actually share another slide deck with you later that explains it clearly. But essentially, when we want to sense the current bit, to see that if it flows or not, there is a sensing circuitry there.
Oh, it's a sensor before whatever it was.
Yeah, there is a sensing circuitry that if you initialize that circuitry the other way around, you're gonna read inverse.
Okay.
It's not that magic when you see it, but yeah, you can do this. Was that interesting?
Yeah, it was. Yeah, I'm just
yeah. Where did you study for your bachelor's? Was that in South Korea?
I'm still in my bachelor's. I'm studying at the University of Slovenia.
Oh, okay. So you're like
I'm an exchange
student. Good.
I enjoy the class.
Yeah, good. Our pleasure.
It's unfortunate that Jan is not here today.
Oh, why? What?
He's running away from my questions. No, I'm just kidding. We just had a discussion yesterday and I would love to continue it.
I see. Okay. We have 3 more papers to discuss, and we have 45 minutes. I think it's doable because these 3 are not that detailed. Sorry?
I think 15 industry conference.
Yeah, exactly. Yeah.
I have a question.
Yes.
So, I mean, obviously, you've already talked about it, that we should have data-driven, data-aware, data-centric systems.
Yeah.
So, I mean, looking also in the future, Neumann's architecture might be, or probably even is, not the ideal solution to it. And there are a lot of emerging technologies in that area, right? So, I mean, even Onur, I think in 2009 has worked at PCM,
yes.
phase-changing memory.
Yes.
And now there is ultra very exciting with like quantum physics and everything.
Yeah.
If you had to pick one direction you want to work in, only one, what would you say is the most promising for you?
Yeah. I mean that's a very hard question, and actually it's very subjective. I'm quite excited about data-centric. I would say I'm quite excited about intelligent architectures. I mean the line of data-centric, data-driven, and data-aware. I really enjoy actually data-driven projects that Rahul and Rakesh, for example, they are driving. But data-centric is something that I'm focusing personally more, as a, if the research that I want to lead. And these days I'm focusing more on a storage system. But that's not because I want to, only select that line. I think all of them are quite exciting and they are the future.
This is just an author, but they're also like completely different systems in that sense, like neuromorphic architecture that try to model the computer as a brain. Do you think that's promising or?
Yes, I think actually, so the thing is that going to the future, we really need to, empower more specialized processor or system design. So we have a lot of different computation capability, and I think we really need to benefit from all of them, kind of, It's also like about also quantum computing. So people usually, they don't really envision quantum computing as a replacement of general purpose computing. It's going to be also more or less specialized for some applications. So it's just about that, you really need to benefit from everything that we have, because these days we are really limited by the energy performance and all these worldwide, let's say, problems that we have. So yeah, we need to benefit from everything, let's say.
Yeah, that's fine. But still, you didn't answer the question. First of all, completely.
Yeah.
Don't want to hurt someone's feelings here in the room.
Yeah, I try to be politically correct.
Yeah, thank you.
Yeah, sure. Okay, but no, if I want to say I want to pick one of them, is also not scientific.
Yeah, definitely.
To be honest. Okay. So one paper that I'm going to discuss after Flash Cosmos is not related a lot to, let's say, storage-centric computing, but it's actually something that I think we really need that going through the future, that we enable more and more storage-centric computing. Because I showed that, for example, for ISP, we are limited by the, let's say, the internal parallelism that we have inside the storage. So traditionally, storage systems are designed, the parallelism that we have internally, they are, I would say, that is good enough to support what we need for normal operations of storage, and also some internal tasks of storage, like the garbage collection, this stuff. But if you want to also do computation inside the storage, then you really need to double, you need to revisit all these things and see, is it what we have there as like the internal parallelism, is it really enough? So that's the reason I want to present this work, Venice, which we improve. Basically, we propose this Venice to, improving the solid state drive, which is SSD, parallelism at low cost via conflict-free access. So it's a work that we, proposed, like the interconnection network is presented very soon. That is an interconnection network that provides conflict-free accesses. I would say not theoretically, but practically, conflict-free accesses, and that provides a lot of good performance. But that kind of design can be really useful. It's very useful for the moment that you want to do computation inside the storage. Okay, so the key problem about this work is that past conflicts in modern SSDs. So multiple flash memory chips are connected to the SSD controller using a shared channel. Remember that shared channel that I showed, that basically several flash chips are connected to the storage controller. And I/O requests attempt to simultaneously access the flash chips using a single pass. So that's the problem, If you can basically distribute your I/O accesses across the channels, then you can benefit from the parallelism. But if your requests are, because of your bad luck, they schedule to the same channel, then they need to be serviced serially, and you cannot benefit from your internal parallelism. And we have this problem of past conflict, basically. So past conflicts cause a lot of, I/O requests to be transferred serially on the shared channel, and that limits SSD parallelism and overall performance. So let's see about the delay caused by past conflict with an example. So this is a flash controller, let's say, that we show a channel number, like channel 0, and there are some flash chips connected to that channel. So we have, let's say, two requests, read request 1 and read request 2. And so both of them, they want to basically approach these two. I mean, one of them wants to, target flash chip 0 and the other one 1. So we have pass conflicts. So the thing is that we have been working a lot in order to make sure that requests are basically targeting different flash chips. But the thing is that targeting different flash chips does not necessarily cause conflict-free access. So those flash chips, they might be actually connected to the same channel, and then you have this pass conflict problem. So when you have a pass conflict problem, you can actually you have this you need to serve serially, and that's the problem. But when you have different channels, ideally you can actually reserve read request to read requests completely in parallel, and you can serve in parallel and basically save a lot of time. Clear, right? So we basically observed that pass conflicts increase the average I/O latency by 57% in our experiments on a performance optimized SSDs. And that can be also, I mean, only if you have, let's say, two requests that they have pass conflicts. But it can be, at some point, the average latency has been increased much longer as well. So the performance overhead of pass conflicts increases by 1.6 times in our experiments for high I/O intensity workloads. So there were some prior approaches so they haven't really designed for this problem, but you can actually also repurpose them to be used for this problem. So basically there are these boards, network SSD and network on SSD, that basically they try to have, so in network, sorry, so this is the baseline SSD that you know. So in another work that has been proposed in Micro 2022, this one, network SSD, we have this packetized SSD architecture, that what they do is actually they wider shared channel. So the bandwidth of shared channel is now twice. So definitely it can reduce the overhead of conflicts, but it cannot solve it, fundamentally. This is also another design, like a packetized network SSD, that has been proposed in this network SSD board. They added some, vertical channels together with horizontal channels. So now we have, so every, let's say, every flash chip is connected to flash controllers by 2 passes, and they actually reduce the likelihood of basically pass conflicts, but they haven't, make it. They couldn't really fix it fully. And this is also a network on SSD proposal, that they use a network on chip, so-called like mesh architecture. And instead of channels, they have some links that they are, they connect flash chips to the flash controller. But unfortunately, packetized network SSD and network on SSD, they do not effectively utilize the pass diversity. So that's the thing, in this architecture, we have 2 passes. In this architecture, we have much more passes. But if you are not intelligently utilize those passes, you cannot really, basically resolve the conflicts. And most of them, unfortunately, they incur large area and cost overheads to the flash chips. So our goal is to fundamentally address the pass conflicts problems in SSD by increasing the number of passes to each flash chip. So we want to provide pass diversity at low cost. And at the same time, we want to effectively utilizing the increased pass diversity for communication between the SSD controller and flash chips. We call it Venice. That Venice is a low-cost interconnection network of flash chips in the SSD, and provides conflict-free pass reservation for each I/O request. And we also use it, so we enable this conflict-free pass reservation by a non-minimal fully adaptive routing algorithm for pass identification. Okay, so let's see, and let's learn about this Venice with some examples. So these are flash nodes. We call them flash node. And links. Each flash node consists of a flash chip and a router chip. So that's the main difference between the design of network for Venice and Freiburg. So we don't basically integrate router chip or router die inside the flash chip die. So we separate them, and that can cause a lot of actually saving in the complexity. Because flash chips, the number of IOs for flash chips are really hard to increase. So the good thing with this design is that you still communicate with flash chip with only 8-bit IOs that they have currently. But the router chip is the one that is placed inside the network and can have connected to several links and provide a higher number of IO feeds. So Venice provides increased path diversity at low cost. That's actually the reason that it is low cost. I mean, that's not all the reasons that is low cost. We also did a lot of things to make that router chip so simple. We will see a little bit about it, but I will let you guys check the paper if you want. And another good thing is that we have no modifications to existing flash chips in Venice, and that's a good achievement. So imagine that this is the target flash node. Basically we select a flash controller, and we send a scout packet to that target flash node. And this scout packet is a very small packet that we send it to the target flash node through the network. And the scout packet, when actually traversing through the network, it reserves the path to the destination. And then use that reserve path to basically return back to the flash controller. So the reserve path is actually bidirectional. So then we have this reserve path for IO request. And the moment that you have this reserve path, you can easily send your data to that flash memory, flash chip, without any conflict or anything like that. So the thing is that one of the key reasons that we can have a low-cost router is that we don't need large buffers. If you just send your packets of data through the network, so they're gonna at some point they might be blocked in the network, and when they are blocked, you need to somehow you can either misload them using some bufferless router design, or you need to buffer them somehow, right? So, and these packets are quite large, like 8 kilobytes of data or 16 kilobytes of data. So if you want to really buffer them, you need to have a lot of buffer per router, and that's not really cost efficient. So with this path reservation, we basically eliminate path conflicts, and we provide conflict-free IO transfer. And basically, we also get rid of buffers as much as possible. So yeah, now I'm just summarize Venice, but I don't have more slides about Venice in this presentation, but I will let you guys to check the paper if you're interested. So Venice mitigates path conflicts by efficiently utilizing the path diversity of the SSD interconnection network, and improve performance by 1.9 times and 1.5 times over the best performing prior on performance optimized and cost optimized SSD. So we configured our baseline for 2 types of SSDs, that performance optimized and cost optimized, and we observed improvement for both of them. And we observed that it can reduce energy consumption by 46% on average over the most efficient prior work. And it is low cost and it requires no changes to commodity flashes. So that's Venice. Yeah.
I guess the performance of Venice very heavily depends on what path we reserve, right? On what path we reserve for the packet to go on. So how do we actually choose which path the packet reserves on? Because probably there can be smart algorithms or also algorithms with a lot of overhead that decide that.
Yeah. Let me get back to this slide. So I don't have more detailed slides about this scout packet in this slide, but I can explain as much as I can in this figure. So first of all, I want to correct what you said. The moment that you reserve a pass, no matter how, for that specific transfer that you want, if you can reserve a pass, we are not really worried about how long that pass is. we mostly care about basically whether or not we can reserve a pass. And that pass can be actually so minimal pass like this, but sometimes you're already blocked in the network, your network is so crowded, and you really need to find some, let's say, non-minimal pass. And that's the reason we are using non-minimal adaptive routing, something like that. We intelligently use non-minimal adaptive routing, fully adaptive routing, in order to, reserve pass as much as possible. And why the number of hops, or let's say the length of that pass is not that important, because our the packets are quite large. It's like 16 kilobyte of data, for example, and these channels or links are quite small, like 8 bit. So you need to wait for the first 8 bits of data to go hop by hop, step by step to reach to the destination. But after that, you will receive the rest of the packets or message per cycle. So in the end, you have a pipeline. So we don't, and since the length of packet is quite large, we are more or less bottlenecked by the amount of data that we are sending. So we are not bottlenecked by the number of hops that we are taking. So that's the thing. But the way that we reserve a pass, so we send a scout packet to the network, and scout packet tries to basically goes to the next hop and tries and reserve a pass basically here. For example, on this flash chip goes to this flash chip and reserve this pass. From this part, we do a routing function for that scout packet to the destination. There are some basically response that, okay, these links, if you take, you're going to be in the minimal pass. There are also some links that if you take them, you're going to be in the non-minimal pass. So we always try to prioritize minimal pass over non-minimal pass. But unfortunately, sometimes minimal pass are not available. I mean, here is available, but imagine that's not available. So we need to take non-minimal pass. And then we reserve the non-minimal link that we take. And again, here also we do that random, basically that routing function again and again. And at some point, we actually, this scout packet cannot reach to the destination and get back to the misroute and get back to the previous router. And we need to release what we have reserved before. It's actually a little bit complicated, but it works.
So can you explain how the router chip itself works? Because it obviously is considered a lot of things at the same time. So like what's the penalty in terms of complexity and area compared to the regular structure?
So the router chip that we have here is quite simple, as I said, because first of all, we don't use buffers. Our buffers, they are quite small here. They are just large enough for a scout packet. And a scout packet is like 16 bits, as far as I remember. So our packets are quite small. Our buffers are small. A routing function is also so simple here. So we just randomly select. It's just so simple. And we don't have also virtual channel. I mean, these are also so specific to the field of interconnection network. Some of this terminology might sound a little bit weird to you guys. But yeah, basically the cost of router is so low here. But the thing is that the router die is so small, but when we want to package that router die in a chip, because remember that in each flash node we have flash chip and router chip, right? And that router chip actually here in this example, imagine that we connect the router chip to 4 links and also one IO bus, right? So each of them is 8 bits. So at least from this figure, you can see that the router chip needs to have 40 IO pins, right? And that's when you want to basically make that happen, you're bottlenecked by the widths between the IO path, basically, So that's the bottleneck that we have, basically the overhead that we have for router chip. So our analysis showed that the old router chip that we have, they increase the area of the chips inside the storage subsystem by 10%, actually. But our links are much smaller. They are lower, smaller size compared to shared channel bus. And overall, we observed that actually so we didn't actually combine the area reduction of interconnection and area increase of chips. So we report them separately in the paper. So we say that for the chips, we increased the area by around 10%. But for the interconnection network, we reduced the area by, if I'm not mistaken, by 40-something%. So you need to double check the paper. But yeah, so we don't really know because we haven't designed the PCB in that detail. We know the exact area. Does that answer your question? Okay, any other questions? Okay. Okay, now we reached to the second part. I think we have good time. So this is a processing near flash memory that we, briefly also observed here, like before, like ISP. That's exactly what we need here. Again, this is also very similar to processing near memory that you guys have observed, I guess that's last week. That basically we consider memory, as a programming model. We consider memory as a conventional accelerator. So there is specialized compute capability accelerator connected to the memory. It can be very, very close to the memory, like close to every bank, let's say, or subarray. It can be also a little bit further, connected to every chip or connected to a DIMM, let's say. But anyway, the concept is similar. So there is an accelerator which is close to the memory, and you offload a part of computation to that. And we have basically published several papers in that direction. But the work that I'm going to discuss first is actually GenStore, which is a beautiful work that Nika drove for ASPLOS 2022. So it's about the high performance in storage process system for genome sequence analysis. I will only provide a very brief overview of this work. I'm not going through the details of that. So you can actually, we may actually have some talks about this work later in this seminar. Do you have notes?
I want to present it, hopefully.
Oh, okay. We'll see. Okay, so yeah, so genome sequence analysis is critical for many applications, as you know, like personalized medicine, outbreak tracing, evolutionary studies. And genome sequencing machines extract smaller fragments of the original DNA sequence known as reads. And so the first step of basically genome sequence analysis, read mapping, is the first key step that basically we need to align reads to potential matching locations in the reference genome. And for each matching location, the alignment step finds the degree of similarity. We call it alignment score. Basically, these are the differences. And for calculating the alignment score, it requires computationally expensive algorithm like approximate string matching to account for differences between reads and the reference genome. So basically, for this step, we need to read a lot of reads from storage system and bring them to the computation unit because of the Neumann model. And so this computation unit can be CPU or accelerator. It doesn't really matter for this context, basically. But you need to read reads. You need to read reads from storage system to that computation unit. And there are many reads, and that cause a lot of computation overhead. And at the same time, you have data movement from storage, which is a lot of overhead. So they're having many efforts in order to improve the performance of basically read mapping by proposing some heuristic algorithms, designing some accelerators near caches, for example, and designing some filters in order to reduce the number of reads that we want to do computation. And they can actually reduce the computation overhead, but still they need to send data from storage system to the computation unit, and it has this data movement overhead. So the key idea of the GenStore is to filter reads that do not require alignment inside the storage system. So we want to basically filter reads and just send those reads to the computation unit that they really need to, basically really need to do that approximate string matching algorithm. So there are two types of reads that we don't need to do ASM for that alignment string matching, approximate string matching. Those reads that they have exactly matching positions, so we don't need to basically this expensive approximate string matching during alignment. And there are some reads that they are non-matching. So in the end, they are not going to be matched or aligned to the reference genome. So for those, we don't also need to send them to the computation. So basically, in GenStore, we aim to specify those exactly matching reads and non-matching reads and filter them and reduce a lot of data. So, but it's actually, it has some challenges. So we want to do it inside the storage, but it has some challenges. Grid mapping workloads can exhibit different behavior, and also there are limited hardware resources in the storage system. So we basically, by addressing all these challenges, we propose GenStore that filter reads that do not require alignment inside the storage system, and that provide a good computation overhead as well as data movement overhead. So we really significantly reduce data movement overhead. And GenStore provides significant speed up between 1.4 times to 33.6 times, and energy reduction at low cost. Any questions about GenStore? So again, it's about reducing your data inside the storage. So your data that you want, your reads here in this context that you want to do that ASM algorithm on them, they are stored inside the storage. You want to reduce that amount of data before transferring them to the storage, to the CPU or GPU or accelerators. So you reduce your amount of data using this filtering algorithm. And your filtering algorithm basically selects exactly matching and non-matching reads, basically, and then filter them out and send them what the rest of reads to the computation unit. So, but this work is actually we only do instant. You have a question?
No.
This work basically implements like filtering inside the storage, but we have actually done another work in this context for metagenomics. It's like a storage-centric design. This work will appear in ISCA 2024. Just got accepted. Congratulations to Nika. So we call this work METIS, high performance and low cost metagenomic analysis with in-storage processing. So what is metagenomics? Metagenomics is the analysis of genome sequences of diverse organisms within a shared environment like blood, soil, oceans. So, and it overcomes the limitations of traditional genomics. So bypasses the need for isolating and culturing individual species, and addresses clinical environmental challenges where culturing is impractical. So that's the importance of metagenomics. And it has led to groundbreaking advancements like precision medicine, understanding microbial diversity of an environment, discovering early warnings of communicable and things like that. So there are several key steps of the metagenomics workflow. We first need to do sequencing that extracts the genomic information of all organisms in a sample into digital data. And a sequencing machine generates randomly sampled inexact fragments of genomic information that we call them as reads. And then we do this base calling that we convert the raw sequencer data into sequences of characters like ACGT. And then we need to do analysis for basically metagenome. And we want to determine the species like present and absent in the sample. That's one of the key tasks of metagenome. And also, we want to determine the relative abundances. So we want to know how many basically microbials that we have in our sample. So by accelerating the analysis step, metagenomic analysis is typically performed much more frequently compared to other two steps, like the sequencing and base calling. So you do sequencing and base calling, and then you want to do analysis several times. So it really makes sense to accelerate that process. And even for one round of analysis, the analysis step bottlenecks the end-to-end performance and energy efficiency. So even if you only do analysis only once, this is the analysis is the bottleneck for the performance and energy consumption. So we really need to accelerate it. And due to rapid advancements in sequencing technology, the gap between sequencing and analysis is widening. That's exactly what I also showed in the beginning of this lecture. And another important thing here is that people actually have been trying a lot to accelerate metagenomic analysis by trading off accuracy. Basically. You know, they provide much lower accuracy, but they increase performance. But it's really, if you really need high accuracy, but at the same time high performance, there is no technique that actually can provide that. And in Megi's proposal, we try to bridge that gap to provide high accurate and high performance at the same time metagenomic analysis using a storage-centric design. So this is another figure of metagenomic analysis. So basically, these are the sample reads that we have, So we read some k-mers from them. I'm not going over these details, and I think you also have some understanding of k-mers from the genomic lectures that John presented. So basically, we need to search or query these k-mers from the database that we have, and then we to do presence and absence identification. And then we basically provide these tax IDs in the sample, and then we have this abundance estimation. That's the whole process of metagenomics. So the problem is that the I/O impact on end-to-end performance becomes even more prominent in emerging systems in which other bottlenecks are alleviated. So the case study on metagenomic read dataset, tools with different access patterns to the database. So we use different metagenomic tools, or let's say metagenomic applications that they basically work with the problem that we wanted. And we use various state-of-the-art SSD configurations. So we use both cost optimized, let's say capacity optimized, and high performance optimized SSDs. And we observe that the I/O data movement overhead causes significant performance overhead. Sorry, animations here were just screwed up, but that's fine. Okay, so the challenge and goal is that while in-storage processing can be a promising direction, none of the existing approaches, approaches of the current tools that we have for metagenomic, the current implementation, none of the existing approaches can be effectively implemented inside the storage system due to limited resources available in the storage devices. And our goal is to improve the performance of metagenomic analysis by reducing data movement overhead right from the storage system in a cost-effective manner by addressing the challenges of ISP. So we propose Megis, the first ISP system for end-to-end metagenomic analysis. Sorry. It's actually a cooperative ISP. It's cooperative ISP that we do some computation inside the storage system, and as well as some computation inside the host system. So it's actually very like storage-centric design that you use this paradigm of in-storage processing to design a system, basically, that you do some part of your computation inside the storage and use some part of your computation in the host system, and you connect them well, you basically pipeline them well, such that you don't miss a cycle, you don't waste any cycle in the computation. So it's a cooperative ISP, and it enables an efficient pipeline between the host and the storage, and it maximally leverages and orchestrates their capability. So for evaluation with inputs with low, medium, and high genetic diversity, we observed quite a good speed up compared to performance optimized baseline. This is the performance of the algorithm that provides the best performance. So you can see that we compare against two baselines. One of them is performance optimized baseline, which uses high performance algorithms or implementations, but they are relatively provide lower accuracy. And also we compare against accuracy optimized baseline, that they provide high accuracy, but unfortunately low performance. So even compared to the performance optimized baseline, we have good speed up. And compared to accuracy optimized baseline, our speed up is much more. And we also provide good energy reduction compared to performance optimized and accuracy optimized system. And also, so we don't have the results here, but Megis provides high accuracy and at low cost. So the area overhead of Megis, that all the accelerator that we have inside the storage, they are relatively low cost. So yeah, hopefully we will have longer talk about this paper. But I just wanted to share some brief information about this work as well today. Any questions before I conclude this lecture? Okay, good. So let me conclude with some remarks. Basically, we must design systems to be balanced, high performance and energy efficient, all at the same time. And so today, systems that we are designing or we have been designing, they are not really balanced. So a lot of resources that you have just for storing data and communicating data or moving data, and your processing capability is just happening in some small units, like a processor, GPU. As I said, even inside the CPU also you have a lot of nodes. So your ALU is very small compared to the whole system that you do computation. And so it's really important to have a balanced system design. I mean, using that basically principle in your design, just using different, do computation like everywhere. I mean, whenever it makes sense. And also design high performance and energy efficiency all at the same time. So we don't really want to trade off performance for energy or the other way around. And in order to achieve that, we really need to go through this paradigm of data-centric, data-driven, and data-aware architectures. And that enable computation capability inside and close to memory storage. And this can lead to orders of magnitude improvements, enable new applications and computing platforms, enable better understanding of nature, and so on and so forth. And future of truly data-centric computing is bright, but we need to do also a lot of research. And we can get to that step by step by revisiting the computing stack. And this is basically the way to get to fundamentally better architectures to use all these data-centric, data-driven, and data-aware architectures. Okay, thanks a lot for your attention. Any questions? Happy Easter break, and we're gonna, I guess we will meet again in 2 weeks.